Okay, so this is actually hemoglobin. Most of you probably know that hemoglobin is in your blood, right? And what does it do in your blood? Well, there's a very special function. It transports oxygen through all the cells, sorry, not through, but to all the cells in your body. That's what it does. So let's use this protein, hemoglobin, as our example for what is chemistry in its definition. What is the composition of hemoglobin or your blood? All right. The first thing is composition. Well, proteins are actually made of these things right here that are like swirly things. They're called alpha helices. These are all random coils, and they're all made of very specific things called amino acids. We'll talk a lot about amino acids later on in life. I mean, later on in the semester, not in life. But they're all amino acids. But mostly, the most important thing that hemoglobin is actually made of is actually in the center. And in the center is a molecule called Hem B. Alright? So let's take a look and see what Hem B actually looks like. Hopefully my writing didn't cover anything up. Oh, it did. That's okay. That's not the important part. So this is the structure of Hem B. We answered that question now. Structure. It's actually a very important structure because it's what we in chemistry call a tetrapyral molecule, because there are these guys right there with the double bonds, the 5-membered rings with the nitrogen side. Those are all called tetrapyrals. Sorry, actually they're called pyrols, and there are 4 of them, right? And that's why it's called a tetrapyral molecule. Interestingly, when I was in grad school, I did a lot of work with tetrapyral molecules. The one I studied was actually called luciferin, and it actually made, when it bound with an enzyme, a special enzyme called luciferase, it actually glowed blue. So that was a pretty cool protein right there. The most important part of this heme, though, is this guy right here. It's an iron that's in the center of the heme, right? And that iron likes to interact with oxygen. So that's the properties. Interaction with oxygen, right? That's what the heme does there, right? You take a close look at that heme, and you see a 2 next to it. What does that mean? That 2 actually means that the iron has a +2 charge, right? But it likes oxygen, and oxygen likes it, right? So when you bring oxygen into the mix, the iron actually becomes a +3 charge, right? Why does that happen? Well, it's because oxygen is, I don't know if you remember this or you have heard this before, but oxygen is actually very electronegative. What does it mean to be electronegative? Let me spell that right. Electronegative. It means it loves electrons, right? It'll take them from other atoms. And here it took an electron from iron. So when you take 1 electron from iron, it goes from a +2 charge to a +3 charge, because it's 1 electron less now, and electrons are negatively charged, um, which is very interesting, right? It's also very interesting because this is actually the difference between deoxygenated blood and oxygenated blood, right? Oxygenated blood has an iron, an Fe3 +3 charge, right? An iron with a +3 charge, whereas deoxygenated blood has an iron with a +2 charge. And you can actually see this with your eyes, because a deoxygenated blood actually has a dark red color to it, whereas oxygenated blood has a very bright red color to it. Bright red color to it, right? Very bright red. These actually correspond to wavelengths of light um, in the visual spectrum, and the dark red is actually 940 nanometers, and the bright red's actually 660 nanometers. Interestingly, I was talking to you about luciferase and luciferin earlier. Luciferin, when it turns blue, that bright blue color I was talking about, it's actually 475 nanometers. Is blue. Very bright blue, right? So back when I was in college, I had a professor named Dr. Chastain, and he would always ask us what our favorite color was. Well, he didn't want you to actually tell you what the color was. He wanted to know what the wavelength was. So he would always say that his favorite color was 663. He didn't say 666 because that'd be kind of weird. So it was 663, right? What is 663? Well, actually, 663 is super close to 660 here, right? So 663 is then what? It's red, very bright red, right? So people ask me what my favorite color is now. I always say, oh, it's 475, which is blue. If you take a look at the visible spectrum, you can figure out what your favorite color is too. Why is that even important? Well, have you ever gone to the doctor or gone to the emergency room and had to use a pulse oximeter? I don't even know how to spell pulse oximeter. Is that how you spell it? There we go. It was the meter part that I didn't know how to spell. Anyway, a pulse oximeter actually works on this change in wavelength right here, right? This change and the difference between those two numbers is how a pulse oximeter, one of those things that goes on your finger that determines how much oxygen your blood has, right? The difference between that number, 940 and 660, is how a pulse oximeter works and tells you what your oxygen content is. So next time you go to the doctor, take a gander at it. That's why there's you see a little light in there, and it's a little red light that actually can go penetrate your skin and see what color your blood is, and that's how it tells how oxygenated your blood is. Kind of interesting.